Welcome back, everybody. The topic today, as you can see from what we have on this tentative schedule, is to try to now summarize a little bit the recurrent neural networks and the long short-term memory. And then we are going to dive into autoencoders, which is going to keep us busy for both today and also next week. We are most likely going to start with generative adversarial networks the week thereafter. I also wanted to just highlight for you the basic website of the university, and you can then look at the tentative schedules which we have. So we last week we actually looked at the recurrent neural network and we started to discuss the projects, and I want to come back a little bit to this. And you find obviously the videos of the lectures and everything. And also, if you look at the topic this week, we are going to summarize these RNNs, and then we will start the discussion of autoencoders, which is another very popular method. This is going to bring us in touch with a dimensionality reduction method, which is called the principal component analysis. So we can actually show that for a specific type of autoencoders, this is the same as the dimensionality reduction which we have in the principal component analysis. And that means it's going to be useful for us to also look at the principal component analysis. So this lecture is going to be a mix between a reminder of what we did last week, a summary of this long short-term memory, and then the start of discussion of the autoencoders. And then next week, I would like to suggest that we spend more time on autoencoders and look at how we can write the codes for the differential equation problem, which we are looking at. And then when we're done with that, we will then most likely begin with GANs, and that will be the last deep learning method, which we will cover in this course here. So I just wanted to quickly also remind you of where you find the videos of the lectures. That would be here. Or alternatively, if you go to the main GitHub page, you will typically find the videos of the lectures in different places here. So what we had here was a collection of the topics from February 27 to March 10. And the lecture material is then what we covered last week is actually in the video, which you see here. So let me switch back to the Jupyter Notebook, and I'm going to use that one for a good fraction of the time today. So let's just bring this up. And if we look at the topic for this week, I wanted to give you a quick summary of the RNNs, which we discussed last week, and we're also going to look at a little bit more about the details of this long short-term memory, which we only covered hastily last week. The material on autoencoders is something you can find in the textbook by Goodfellow et al., and that will be chapter 14. And you find also good implementations of many of these methods in Jeroen's book. And there are links here to different tutorials on autoencoders as well, if you want to look at them. So if we now go back to the topic which we have, which we covered last week, for project number 1, and for those of you following the differential equation path, the codes which are also included in today's lecture, which I'm going to remind you a little bit of, is something which we can then use in the solution of differential equation. So the kind of idea is that when we now look at the differential equation, I mean that specific part, I would like to recommend that when we have done the neural network calculations, we switch to RNNs and try to see if that gives a better reproduction and prediction of this for the solution of differential equations. And then when we are done with that, we can then, as we will do next week, we will switch over to autoencoders and see how we can program autoencoders in order to solve the differential equations. So we are going to use the differential equations as the example. Now, feel free to chip in, and if you have other suggestions which you would like to propose, feel free to do that. So today, I wanted to first set up this summary of RNNs, and then say something about the long short-term memory. And I would also like to suggest that since you now have split into working groups, you could then look at the implementation of RNNs and neural networks for the solution of the differential equations. And then just try to compare the two. And that will be part of the project anyway. So that's about the project work. And next week, I would like to use this material about autoencoders and show you how you can set up autoencoders for solving the differential equations which we have in the project. And then we should be pretty fine with at least 3 main methods from deep learning, and where the autoencoder method is actually an unsupervised method. But let me remind you of what we did last week. So when we think of this recurrent neural networks, what we ended up with is in general a network which is purely deterministic. So we have an internal representation which is given by real valued vectors and matrices. And in a traditional neural networks, assume that every input is independent of each other. But with this kind of sequential data which we have now at a given stage t, you can think of t as a time, that would depend on the input from the previous stage t minus 1. And we would have these weight matrices u, w, and v that connect the input layer at a given stage with a hidden layer, and then the previous hidden layer with the new hidden layer, and the hidden layer connecting with the output layer at the same stage. And you also have an input x at a given stage. So the output from the hidden layer would then be modulated by a function h of t, which now is given by this result h of t, which is given by function f, which is often rewritten in terms of a tanh function. And then you would have the weights in the matrix U, which connect the hidden layers with the input x of t. And then we have a matrix W, which connects with the previous hidden layer, plus some bias. And then we have an output, which is given by a function G, which then has a weight matrix, which multiplies the output from the hidden layer, and plus a C parameter, which is typically a new bias parameter. And the output from the training at a given stage is in turn compared with the observation through a chosen cost function. And this is the quantity we want to optimize. And for this function G, which you see here, it's pretty standard to use any of the the activation functions. It could be a sigmoid, it could be a relo, it could be a softmax if you are dealing with different classes to classify. And the parameters are trained through the so-called backpropagation algorithm. So the thing which we saw last time is that this kind of implementation is an implementation which normally is difficult to parallelize. It's also an implementation which is extremely memory requiring. And that means that we are always looking after ways to reduce both the memory requirements and also the number of floating point operations. So it gives normally this kind of standard approach where you train with a backpropagation through time is an approach which gives pretty good results. Your hidden layers can have one or more hidden layers, so you can have a deep neural network inside the hidden layers. But often what you will see is that just one hidden layer makes the job normally. These are things you can play around with, as we will see in the examples a little bit later here. So let me bring back the slides from last week, which we discussed. And if we then look back at what we said, if you think now of a standard neural network, the basics is that you would have some input X, you have some sets of hidden layers, and then you have an output which is compared with your targets. But now what you have is an input at each stage, T, and you can think of these stages T as a time step if you have a time series, which is a very common problem in the natural sciences, like when we're solving differential equations. You could then, when you look at this, when you unfold it, the standard approach, which we discussed with the back propagation through time, is that you have an input here. You at each stage you get an input. You have an input from the previous hidden layer, so that keeps track of the memory. And then this input is fed in here, but this input produces now an output here, which is then sent out here. So this Y is your output of the given stage, and this is compared with the target values or the measurements which you may have at a given stage. So what you have as data, and this is these are the data which we would have from the differential equation. So we would have the inputs at a given time step, and then we have a specific output, which is the solution of the differential equation at a given time step. And that is then compared with the output of your neural network. So this H here could be one simple hidden layer, or it could be many hidden layers. So when you then unfold it, you could have then a multi-layer recurrent neural networks. So these could also, if you have a classification problem, these could also be convolutional neural networks. So you're not hindered by you being, you're not limited by having just a standard feed-forward neural network inside here. And what you see now is when you look at the inputs, so the input comes from the previous hidden layer. So that's where you have the memory from previous stages. And you also get the input here, and that feeds to an output. And you can have many different types of, so actually the output from this stage here is fed in here, but it's also fed in here to produce the output, which is then sent to a cost function and compared with the final target value. So that's the basic setup. And in our case, the targets are going to be the output from the differential equation solver at a given stage, and then the inputs would be the X values or the input values from, let's say, an external force which is acting on the system, just to give an example. And you can have different types of sequence modeling. And the basic algorithm is the so-called back propagation through time. So you need to train now weights here, which connect, sorry. So we have weights which connect the previous hidden layer with a new one. You have weights which connect the inputs with the hidden layers. And then you have weights which connect the hidden layer product H with the output layer. And the output layer produces your output, your model output Y, which is then compared with a target value through a cost function, which we want to optimize. So you would have a kind of net input to this H, and there is an activation function here. And normally this activation function is a tan-H function. That's the most standard one, which is being used. So you produce an output, and then that output is then fed into the next stage. So you would have a Z of Y, which is now the output from the hidden layers. And that's multiplied with this weight function, which then produces the final output through a new activation function. And you can obviously play around with different types of activation functions. And that means also you will have different optimizers. And then you have a back propagation through time. Your cost function is now, or loss function, is the sum of the individual ones. And you're taking the derivatives and computing the gradients and training the weights by back propagating through time. So the feed-forward stage is pretty straightforward. You initialize the weights and the biases, and then you produce an output, and then that output is compared with the target values. And the back propagation through time means that you have to calculate the different derivatives, and the different derivatives with respect to the parameters, the different weights, are then just given by this repeated application of the chain rule. And you would have a back propagation through time, And one of the problems is that if you now look at the way we compute these gradients are then computed by the product of all these derivatives via the chain rule. And this is something which gives rise to either vanishing or exploding gradients, as we discussed last week. And this vanishing and exploding gradients, they can be treated in different ways. So for the vanishing gradients, it's pretty common to tune the initial values of the weights and biases. For the exploding gradients, a standard technique is the gradient clipping technique, which we discussed last week. So this is just a reminder of what we did last week. Now, this method is, as we said, it's very memory requiring. So one of the ways to circumvent this is to have this kind of gated units. And there is one method which is called the long short-term memory, which is one of the more popular ones. And it's the way it's done is to design a memory cells, which uses either logistic or linear units with multiplicative interactions. And the information gets into the cell whenever it has a write gate on, and I'm going to show you what this means. And the information stays in the cell so long as its keep gate is on, and information can be read from the cell by turning on its read gate. So let's take a quick look at the way you can set up this, and I borrow some slides from some lectures elsewhere. So let me just bring up that and just find, it should be, I just have to remind myself which one it was. Just a small moment. I just need to see which slides I was looking at. So suddenly let's see now. I think it may be this one. No, it's not this one. So let me just stop sharing and bring up the right slides here. I had too many slides up here. Okay. So let me just bring this up here. Okay. Now I found the right screen which I wanted to share with you. Okay. And you actually have a link to these slides in the beginning of the lectures from this week. And you will also find them in a folder on other lectures. So the whole idea now is to circumvent the problem with the intensive memory requirements, because when you train a recurrent neural network, you want to keep track of the long-range history, because that becomes important when you want to make a prediction beyond the data for which you have fitted the model. So the long short-term memory, the idea is that it should be capable of modeling longer-term dependencies by having memory cells and gates that controls information flow along with the memory cells. Now, I'm just going to give you a superficial view on this, because there are lots of technicalities which we may not need to dive into immediately in order to be operative. So in a certain sense, it's okay just to keep an overarching view on what is going on here. So the idea now is that this should be capable of modeling these dependencies, and you would then have calculations which are done at given instances, and you may have these memory cells at one specific at all instances or stages, or you may just have it at some, and the hope then is that these keep track of the long-term dependencies. So a typical cell which you have, so this receives an input x of t, it produces an output. This output is also fed into the next stage, as we discussed earlier. And this h of t, which you see here, is what is outputted from the network into the output layer, and then compared with the final result at a given time stage or stage. So typically, what these gates have, they contain these cells. They are regulated by some gates. There's something which is called a forget gate, an input gate, and a reset gate, and an output gate. And obviously the output gate is the one which is important for the output to the next layers. And each gates are composed of different transformations with a sigmoid activation type of functions. And often this is either the sigmoid or the tanh function. These are the most common ones. So the way you set this up, the first thing, so you receive your input from the previous hidden layer. There is the input from the external source. So this could be a force which is being applied to the system. And then this is fed into a type of sigmoid function. And it determines how much contents from the previous cell is going to be kept or just erased. And it's a linear transformation of concatenated previous hidden states and inputs. So what you're doing then, if the value here is below a certain threshold, it generates 0. And if it's above a certain threshold, it generates 1. So you can see now that you have a bias parameter to train, and you have the weights here, which link the previous output from the previous layer. And then you have the input layer here. And then you have the weights which are training. The next is something which is called a candidate cell. They are created as a function of the outputs h of t and the input x of t, the one from the previous layer. And these kind of input gates, they decide how much of the values of the new candidate cells are combined into the cell states. And this is often done via a tanh function. So you have a new set of weights you want to train and a new bias set here. And similarly, you have this, so these gates, C and T, and this I is normally given by a sigmoid function. So this gets very, to me, it often has a kind of ad hoc approach in order to just keep track of how much information you want to keep. So you have some information which is depending on your sigmoid function. You put a threshold and you say that, okay, if it's below a certain value, I disregard that information. If it's above a certain value, I keep it. In a way, it's a kind of, it acts like a kind of neuron where you send a signal or not, depending on a threshold value. So it's you can think of it like that, like you sending a signal depending on what is the threshold value. And then there's something which is called an update cell. So the previous cell, which had CT-1, which comes from the previous hidden layer, they're updated to the new cell states by using the input and forget states with new candidate cell states. And this is the way you would simply set it up here. And when you have that, you produce the output, which is fed into the next one. And at the same time, when you want to generate the output here, so you keep track of this cell state C of t, which filter from the output stage. So what you would do then is to simply produce an output here, which is now given in terms of new weights and biases to be trained. And this is this quantity which you have here. And then you have a final output, which is generated from some tanh type of states, which are then filtered by this O times tan here. And that produces your H of t, which is then sent to the output layer and also to the next hidden layer. So the kind of idea is, if you think of this as a kind of dimensionality reduction approach, you're just keeping track of some information, and some other type of information from the previous layer is then disregarded. And in the most general setup is that you have these types of gated circuits. So this is actually a gated circuit, and where you reduce the information which is being stored. And this is one type of approach. There's something which is called also the GRU, which we're going to come back to. What I wanted to show you is more the implementation, which you can set up yourself. And there is an implementation in the Jupyter notebook for this week. So let's go back to the Jupyter notebook, which we have for this specific week, and just look at some of the implementations which can be done by using, so this is just basically a more detailed demonstration. So the first model which we have here is an extrapolation which receives a given set of data, and this data are calculations from a quantum mechanical problem, where you run a full calculation where these parameters you see here, which go in steps of 2, they represent different truncations of effective Hilbert spaces. So this 42 here is the most time-consuming calculations, which actually took 10 CPU hours on a serial node. And the calculations which you see here, they produce the energy of the lowest lying state. So everything you see here is a result from a many-body calculations in quantum mechanics, which in principle should give you the best possible approximation of the ground state of a given system. So what we are going to do now is to use a RNN to make a extrapolation. So we're going to train the network for just some of these values. So in a sense, we are using the RNNs as an advanced extrapolation method. This is perhaps not the best case, but it's not so different from what you're going to do with the differential equations. And I'm actually pretty curious to see how the recurrent neural networks work on the differential equations which we have at hand. So my suspicion is that as long as you have periodic boundary conditions, periodic solutions, not periodic boundary conditions, but periodic solutions, the extrapolation scheme is going to work pretty well. So in this, for this case here, I'm just formatting the data. So I'm just formatting it so I can use it with the recurrent neural networks. So this actually, this function which you see here is not that interesting. I'm setting up the simple RNN, which basically gives us the back propagation through time. And when I set up the RNN here, which is done here, I give the input values which I want to produce, and then I define an RNN, which is a simple RNN with a given number of hidden neurons. I specify later here the type of network which I want. I give the model inputs, and then I use the mean squared error, which is the cost function I want to optimize, and then I have Adam as an optimizer. And if we just set this up here, let me just rerun it. And now I'm going to make the predictions on the new data here. And you will see then that these are just reordering the equations. I make predictions, I train the network. So this is how I would test it. And you will see now that in this specific case, I have only one hidden layer. I get something like 40,000 parameters. And I'm running over a certain number of epochs. And as we saw last week, we can now actually get a pretty nice prediction. So the orange area, which you see here, and I think this color is orange. I always have problems with some colors. I believe it's orange. Please correct me if it's not orange. But this area here, up to this parameter with 24, this represents the quantum mechanical degrees of freedom I have. This is what I use to train the data. And you see that in this specific case, the prediction I make outside the region where I have trained is actually pretty decent. And it has a mean squared error, which goes like 10 to the minus 4, roughly, which is pretty good. So that's the global mean squared error here, when I've collected all the mean squared errors. So in my case, I have equally distributed steps, and these are my stages or time steps, if you wish to call them, if you wish to use time as a variable. In our case, this is just a spacing between different effective Hilbert spaces. you could change the neural network and to have a more dense neural network. So you could, in the example which comes here, I have 2 layers. And if I run that one, you will see now that suddenly I have 750,000 parameters. So the number of parameters is increasing quite a lot. I also have more hidden nodes in each layer. So you see that if I now do the training here, what you're going to see is that the results are not that impressive. So I do well on the data I'm training, but in this particular case, you see now that my prediction is pretty bad. And you also see that the total mean squared error is not very good either. So this is a typical example of a problem where we now are trying to make a more advanced deep neural network, and the prediction actually fails on the data which has not been included in the training. You could replace this one with a simple RNN with a long short-term memory layers. And in this specific case, what we are doing now is that we are actually looking at the replacing of the simple RNN, which trains everything by the standard back propagation through time. We are now simply replacing this with a long short-term memory layer. And again, you can specify the activation functions, as you can see here, the type of problem you have, etc., etc. And you can then, when you perform the fit here, you can also use the GRUs if you want to. But the long short-term memory approach is the one which is most used. And in that particular case, you will now see that the number of parameters which we are training is actually getting a little bit smaller than what we had previously, but still it's a pretty large number of parameters compared to the first case, which had only 40,000. Now, in this case, when we now look at the final prediction, so this is with a long short-term memory, it's actually doing better. And you can see that the mean squared error is now 5 times 10 to the minus 3. And it's roughly 1 order of magnitude larger than the one we had with the simple one hidden layer approach. So it's getting better. We can do the same with the GRUs and see if that gives a better results. And in that particular case, if you now look at the final results, this is actually not doing much better. So the wisdom which you can extract from this is actually that you need to play around with different number of layers, different types of approaches to keep track of long term dependencies. And it's not given a priori which approach is the one which works best. So what I would like to say when we wrap up this recurrent neural network part is that for the strategies linked with the solution of the project, I would recommend using Keras as an API, unless you are more familiar with PyTorch and want to use that. And then try to design an RNN, as simple as possible one in the beginning, and see how that works compared with your neural network calculation using the differential equation data. And then simply make an analysis of the different possibilities you can run with a long short-term memory cells. You can just run with a simple RNN, etc., etc. There are lots of optionalities in both TensorFlow and PyTorch. And obviously, if you use TensorFlow, I normally recommend using Keras. So you can look at these examples, and if you want to, you can tailor them to the data from the project or other types of data which you may have. In this case, I'm just using this as an advanced extrapolation method. And perhaps in this case, linear regression is going to do a much better job. We don't know before we have tried it. So any questions so far before we move into the next topic on autoencoders? Feel free to ask questions if something is unclear. Okay, so No questions, not yet. So let me just move to the whiteboard and try to give you some basic understanding of what an autoencoder is. So I'm just going to switch to the whiteboard here. So let's bring that one up. So the autoencoder is a neural network that is trained to attempt to copy its input to its output. So internally, it has a set of hidden layers that describe what is called a code part, which is used to represent the input. And the network may be viewed as consisting of two parts, which is an encoder function and a decoder that produces a reconstruction of the data. So this may sound very strange, and you may ask yourself, what's the point in actually producing an output and try to reproduce the input? It sounds very, how to say, a not very interesting task to do. The hope is that this code part can teach us something about the structure of the data which we have. So this is an example of what we call unsupervised learning. So the basic structure of an autoencoder is something like this. So there's going to be an input layer, and we can now think of having different input nodes. So we have an x1, x2 here, up to some x of d, which is a dimensionality of the problem. So this is the input part. And this transfers the input via a function f into the hidden part, or the coding part. So we're just going to write this. It's normally called the code part. Oops, it was just a moment here. Okay, let me try to highlight that one. So what we have then is a code part which has nodes h1, h2, down to some h of m. And these are connected. So this feeds in information here. The same with this one, etc., etc. So this is the defines what's called the encoder, and it maps. So let me just stay right with words here. This maps x to h via a function f, and this function f is now typically given by some kind of nonlinear behavior of the input x and some weights w. So w plays now the role of the parameters which we want to tune here. So this is the encoder part. Now the encoder part produces now an output, and this output here is now fed into the what's normally called the output or decode part. So let's write this as an output, and this is the decoder. So the intermediate stage is normally called the code part. And in this case, what we do now is that we produce some output, and we have an x1 tilde, x2 tilde, etc., down to xd. And this output is now connected with the part which we have here. And actually, the code part is normally represented by often just one hidden layer. And the idea now is that this output, which we called for x here, so this x tilde is now given by some function g, and it has its own weights w, and then it has the output H from the code part, which is then fed into this X part here. So the goal with this part, so you can think of this G mapping H over to X tilde, and the goal is actually to try to minimize, minimize the error. So if we now just take the least square error, so this is just an example, or the root mean squared error. So what we want to minimize then is this quantity here, argmin, and then we have W and V, which are the weights. We can also include biases if we want to, and we are going to minimize a function which now has n data points, and we start with I equals 0 to n minus 1, and then we want to minimize this x of I minus x of I tilde squared. Now, what we are going to see after the break, because we need to say something about the PCA, or the principal component analysis, because what the autoencoder represents is actually a dimensionality reduction. We're coming back to some of these things after the break. But if we now assume that H is given by a linear dependence between the input X and the weights, so we make an assumption now that we have a dependence like this. So we have a linear dependence. And then we assume also that X tilde is now given by a linear dependence between the weights V and the output H from this coding part. And you see now that this can be rewritten in terms of V times W times X. Now, if you look at the function which we have here, this argmin function, if we now plug in this linear dependence, what we get then is an optimization part, which I'm going to write in a more compact way in terms of the norm 2 here. So this is given by 1 divided by n, and this is the representation of norm 2. So I have a vector x with inputs, and I have a matrix W and a matrix V times, sorry, this should not, okay, x times x here. This is the norm 2 squared of a vector. And this is going to be the same. This is the same as the U actually trying to optimize a PCA where you have a reduced dimensionality. So what you're actually doing then is that you're learning the same subspace which principal component analysis gives you. So this is the same as a subspace. If we make this assumption, so it's easy to show the connection between PCA and autoencoders as dimensionality reduction methods if we take the mean squared error as a cost function and we assume a linear dependence. You can also have a nonlinear dependence, and then we get something which is called a nonlinear PCA, but that's often a little bit more tricky and convoluted to show. So what we're going to do after the break is actually to go through the mathematics of the PCA and see that how that links with autoencoders. So this is the same as the training of a subspace given by the PCA method. And I'm going to use the acronym PCA for the principal component analysis, which we need to define for you, because not everybody has actually studied the PCA method, which is another type of unsupervised learning method, which is then widely used in order to reduce the dimensionality of the problem. So autoencoders, in a way, a method which aims at reducing the dimensionality of the problem, and it has been extremely efficient. And modern autoencoders, they have actually generalized the idea of an encoder and a decoder beyond these kind of deterministic functions which I'm setting up here, and one has actually been able to replace them by stochastic mappings. So you can actually replace these kind of deterministic functions h and this x tilde given by the deterministic functions f and g. You can actually replace them by stochastic mappings. So autoencoders are a pretty rich and lively field. They've been around for quite some time. And after the break, we're going to say a little bit more about the basics of autoencoders. And then we are going to derive the PCA theorem. And then you will see that this is the same as this minimization problem which we put up here. If you have a linear mapping, you can also show it for nonlinear mapping, but it's a little bit more convoluted. So we are going to show this connection so that we see the autoencoders as an unsupervised problem, which leads to dimensionality reduction. And at the same time, the hope is that when we look at this connection between the function, the variable h, and the input x, is that this can teach us something about the structure of our data. I'm coming back to this after the break. So let's take a small break and stretch legs a little bit, unless you have questions, guys. And then we come back at 1:15, if that's okay with everybody. But feel free if you have questions, I mean, unmute yourself or just put a question in the chat here. I'm going to pause the recording now. So I wanted to say a little bit more about autoencoders. So when you look at this figure, which I put up before the break, if the autoencoder succeeds in simply learning this function g so that x tilde is exactly equal to x, this is not very useful, right? Instead, what autoencoders are designed to is actually to be unable to learn to copy perfectly. And usually they are restricted in ways that allow them to copy only approximately and to copy only input that resembles the training data. So that means that the model is in a way forced to prioritize which aspect of the input should be copied. And then the hope then is that it's going to learn some useful properties of the data. And one of the standard techniques which is being used then is something which is called the undercomplete autoencoders. Because if you're just copying the input to the output data, it doesn't sound very useful. And we're typically not interested in the output of the decoder either. Instead, what we are hoping is that training the autoencoder, I mean the encoder part, to perform the input copying task will result in this function h, which we have here. So this specific function, which you see here, this, let me just highlight that one. So this specific function here, the hope then is that this function will result in h, this operation where we now reduce the type of input information to the code part, that will result in h taking on some useful properties. And one way which this is done is actually to constrain h to have a smaller dimension than x. So it means that if we go back here, you see now this x has a dimension d, and here we put h to have a dimension m, and normally we would try to have m to be much, much smaller than the dimension d. Such an autoencoder whose dimension is less than the input dimension is normally called an undercomplete autoencoder, and that's a pretty standard one. And learning an undercomplete representation, that forces actually the autoencoder to capture the most important features of the training data. So this is a kind of hope. It is an unsupervised method, so we don't need to have labeled data here. And the learning process is now simply described by minimizing a cost function. And this is the function which we put up before the break, this specific function here for the just and least squares. where in case if we have a linear dependence in these functions, we end up with an optimization problem which looks like this, where now W represents a matrix which is not a square matrix, so it doesn't have dimensionality D times D, because M is normally chosen to be smaller, or even much smaller than dimensionality D. So what we are doing then is actually to reduce the dimensionality of the problem, and we are then hoping that this keeps tracks of some salient features. And as we will see, this is something which can be linked directly with a very neat linear algebra approach to dimensionality reduction, which is the principal component analysis. So as I said, when the decoder is linear and this loss function is a mean squared error, then what we are learning then is an undercomplete autoencoder that learns to span the same subspace as the principal component analysis. And in this case, the autoencoder is trained to perform the copying task. It has learned the principal subspace of the training data as a side effect. Now, autoencoders with nonlinear encoder functions and nonlinear decoder function can learn a more powerful nonlinear generalization of the principal component analysis. Unfortunately, if the decoder and encoder allow too much capacity, then the autoencoder can learn to perform the copying task without extracting useful information. So theoretically, you could imagine that an autoencoder with a one-dimensional code, but a very powerful nonlinear encoder, could learn to represent each training example with a code. The decoder could learn to map these properties with specific training examples. Now, there are many types of different autoencoders, and if you go into the textbook by Goodfellow and Colville and Benjo, you will find discussions of what's normally called a regularized autoencoder, where you actually have a regularization parameter. You can have sparse autoencoders, and you can add noise to them. You can have the additional regularization terms, etc., etc. So there are lots of nice, I would say, interpretations and applications. And one of the really interesting applications which has been developed in the last years is actually something which is called a stochastic encoder and decoder, where you replace the functions which we put up, this function f and g, with probability distributions, which then encode the transformation between the input data and this coding part, or the intermediate hidden layer part, and the decoder part. So there's a lot of interesting activities, but what we are going to do now is actually to look at the principal component analysis and just remind ourselves about that. And next week, we will look at how we can implement autoencoders to using Keras and TensorFlow, and try to look at the data which we have from the differential equations. And next week, we will also then split a little bit the time between lecturing about how to set up the model and how to actually solve it. So we will have a mix of both workshop, like we had last week, and a lecture where we are more practical in the sense that we are setting up the code examples for studying autoencoders. So what I'm going to do now is to switch back to the Jupyter notebook. And so let's do that, and then say something about the principal component analysis. So essentially what you see in the slides here is just a repetition of what I said. And the example which you see here contains now the mean squared error. Oops, it seems something went wrong with my LaTeX here, so I have to fix that one after we're done here. But I wanted to say something about the basic ideas of the principal component analysis, and the derivations which you're going to see here. They link with the way autoencoders can be programmed if we have a linear representation between the input and the hidden layers and the output, which is given by the decoder. So the basic idea of the principal component analysis is it's an unsupervised method and you're fitting a low-dimensional subspace of the whole space. And if you have a total dimension uppercase D, you want to have a smaller space which preserves many of the basic features. It's based on plain applications of linear algebra, and it has many nice interpretations. And essentially what you're doing now is to diagonalize the covariance or the correlation matrix. Now, the diagonal matrix elements or the covariance matrix elements after diagonalization, they're going to represent the variance. And what you use then is when you order the eigenvalues in terms of descending values, the first eigenvalue is going to be proportional with the variance of a specific feature. And that eigenvalue then represents the variance. And we just keep the variance of up to a certain level. So you could say that I want to keep 95% of the variance. And then you sum up these eigenvalues till you have 95% of the variance. And that is where you would set the truncation. So that means that you leave out features which have a smaller variance, because they are less correlated with the other features. That means that you're actually keeping the features which are most important. So the basic idea now, and if you look at the historical, the PCA, it was first formulated in a statistical setting in order to estimate the principal component of a multivariate random variable. So you have a data set, which we are going to define by a feature matrix X. And this is something which, for those of you who have taken a course on machine learning, you have encountered the definition of the feature matrix. So it's a matrix of dimensionality n times p, where p is a number of features, as you can see here. So p is a number of features which you have. And if you're looking at, let's say, the classification of tumors, these features could be the size of the tumor, it could be the radius of the tumor, it could be the thickness of the tumor, and many other properties which a pathologist uses in order to classify whether this is a benign or malignant tumor. So this is a typical example of a binary classification problem. And you may then, oops, sorry. This is actually my watch, which is listening, and then Siri kicks in sometimes when you talk. So I'm just going to mute that one. Sorry for that. The matrix then has dimensionality d times p, and normally what you would like to have is a set of fewer intrinsic variables where the dimensionality is much smaller. But still, you approximate the data properly. And then the question is, if these intrinsic variables, whether they tell us something important. The PCA is also useful for what we are going to do later, because it's a dimensionality reduction method in case you have data which have extremely many features, and not all features are relevant for describing a specific type of output. So if you now suppose you have two vectors, x and y, so I'm going to use the slides for the rest of the lecture here. I hope you don't mind. The two vectors, x and y, they will have n elements each. So x and y represent some type of features. And then you can define the covariance matrix in terms of the covariance of x with itself. So this is so you could think of n here as the, if you're thinking of this cancer data, n could be the number of patients you have, and x and y could represent some specific features of a given type of tumor. So suppose now the x and y could represent the thickness of the tumor and the surface of the tumor. And the covariance matrix is then something which is defined in terms of these quantities, and the diagonal quantity is just a variance when we use the standard definitions. And observe now that I'm not, when you're using NumPy, it automatically sets this like 1 divided by n minus 1. And the reason for that is that you don't have the exact mean value. So this x with a bar on top is the exact mean value for the variable x, because we only have an approximation to that. So we say that x is a biased quantity. And that's why we have 1 divided by n minus 1. But normally, I'm just going to keep 1 divided by n, because n is normally going to be a pretty large number. But if you use NumPy, just be careful, because NumPy does this automatically with 1 divided by n minus 1. So this is the formal definition of the covariance between x and y. And you see it sums over the variables n which you have. And the variance is just this quantity squared for just one of the quantities. That means that you can rewrite the covariance matrix as the variance along the diagonal elements, and then the covariance along the non-diagonal ones. So the covariance, so this is a symmetric matrix. And that means that we don't need, if we have many features and many variables, we don't need to calculate the covariance for the whole matrix, but it suffices to take the upper triangular part. So the covariance takes values between 0 and infinity, and it may thus lead to problems with loss of numerical precision, especially if you have large values. And it's common to scale the covariance by introducing what's normally called the correlation matrix. And this correlation matrix then is given by the covariance divided by the variance of x and variance of y, and then there's a square root here. So that means that you get 1s along the diagonals, and then you just have a smaller number along the non-diagonals. So it's pretty common to do that in case you have variables which fluctuate largely. So this is below here, they're just examples on how you construct these functions. So if you now, for those of you who've taken a course in machine learning, you may remember that when we did ordinary squares or ridge regression, we could define a design matrix, and this is actually the kind of design matrix which we would feed in irrespective of method. So then we would have the data sets which we have from 0 to n minus 1, and then we have the specific features. So every column vector here now represents a specific features. Just be careful when you set up the covariance matrix, because many people, they tend to invert it in the sense that you have features along the rows, and the number of samples you have, in this case n, are given by the columns. So I'm going to consistently use the columns for features and the rows for the number of samples which we have. So this is our data set. And you know that in case, I know that some of you are looking at specific genetic markers, and you may have some few samples, let's say 100 samples, but you may have 500,000 of genetic markers. So that means that this matrix will become pretty large. And then the covariance matrix may become pretty large. So in that case, doing a PCA is very useful, because you can really reduce the dimensionality of the problem. So when you're setting up this matrix, you can then rewrite it in terms of the column vectors. So x here is now a vector which now contains all the elements along the column. And it has a given vector here where I just look at the transpose of the vector. So this x of I, it now contains the matrix elements. It has n samples, and it has n elements. And in the case here, what you can do now is to calculate the so-called covariance matrix. So C is my covariance matrix, and that is now the matrix which now, when we now go to the general case, so X is an n times P matrix. So that means that you have a P times P covariance matrix. And this is the matrix we want to diagonalize. You can alternatively also set up the correlation matrix, and then you will have 1s along the diagonals. And these matrices are symmetric, both of them. And it's easy to see that they have to be symmetric if you just go back to the definitions of the variance and the definition of the covariance. You see, if I interchange y and x, this just doesn't change the values. So it's a symmetric matrix, and NumPy is one way of using it. And just keep in mind that the NumPy calculates the covariance using this factor 1 over n minus 1 instead of 1 over n, since it assumes we do not have the exact mean value. And there's a function here which allows you to calculate that one through the VStack function, which takes each vector dimension 1 times x and produces a 2 times n matrix W. So this would be the simple case here. When you have only 2 vectors, x and y, produces this matrix, which in turn is converted into the 2 by 2 covariance matrix. And there is a NumPy function, which is called cov here, np-cov. You don't need to use that. You can actually set up your own functions. And in this case, I'm just showing you how you would set it up here. And because you have the data set x here, and this is your y, the output. And then we produce now 2 vectors, x and y. And you get the mean value of x, the mean value of y, as you can see here. And then by the stacking operation, you produce this matrix W. And then that is fed into the calculation of the covariance matrix. And this is the covariance matrix which you get in this specific case. And then you can convert that one into your, if you want to, your covariance matrix. And what I did here is just to do this manually. Oh, sorry, the correlation matrix. So I produce my 2 vectors, x and y, same dimensionality as you see. I rescale them, and this is something which is important because if you now look at the definition of the covariance, this is given by x minus the mean value. So you could now generate a variable which has subtracted the mean value. And that means that you're going to have a scale variable. And that's a pretty standard in the literature here. So this is what we're doing here. We subtract the mean value. Here I'm just doing everything manually. So I'm calculating the variance for x and y. And then I'm setting up my covariance matrix between x and y, x and x, and y and y. And then I set up the matrix here. And this is the matrix, the covariance matrix for this specific case. And you see now that the matrix elements along the diagonals are ones, as they should, and that the matrix is actually symmetric. And it's pretty easy to see that when you diagonalize the matrix, this matrix is going to be a positive definite matrix. So one way to see that is actually to sum the diagonal matrix elements, square them, and sum the square of the non-diagonal matrix elements, and then you will see that the sum, so this is a necessary condition to find out whether the matrix is positive, definite, or no. It means that if you do that, you sum the squared diagonal and compare that with the squared non-diagonal elements, you will see that the squared diagonals in this case, which just gives 2, is a number which is smaller than the squared non-diagonal matrix elements. And that is a necessary but not sufficient condition for having a positive definite matrix. So it's just a kind of way to calculate that one and find out whether it's a positive definite one without having to calculate the eigenvalues. And the covariance matrix and the correlation matrix, they are always positive definite matrices. And this is simply because the variance is a positive number. So you can make it more compact if you use pandas, if you prefer that. So you can see now in this specific case, what I'm doing now is to set up 10 samples. I produce my x value. I normalize it by taking away the mean or just scaling it. I do the same here. I use the stacking function. And then I simply calculate my correlation matrix by using pandas, which has a functionality which is called cor here. And you can see now what the matrix looks like. And then I just print it out here. And this is the final correlation matrix. And again, you see that it's 1 along the diagonals, and then you have a symmetric matrix. I'm just going to skip this case here because now what I want to do now is to show you the links between the covariance matrix and the so-called design matrix. So if you go back and look at the definitions, you can then show with my definition of the feature matrix, or the design matrix, as it's often called, where I have this number of samples which define the rows and the features which define the columns. Then this is given by x transpose times x. And you can easily see that if you calculate the set of the matrix x, in terms of the two vectors here, and then you perform x transpose times x, you will see that this number here is just a variance for the first one. This is the variance for the second element, and the non-diagonal matrix elements are actually the covariances, if you just look at the definition. So this is just the same as us taking these two vectors, x0 and x1, and setting up the final covariance matrix, which we often rewrite simply in terms of x here, and we would skip x0 and x1. So it's a common notation is just to use a more compact notation where we're now calculating the covariance of the design of feature matrix X. And when you then look at the covariance and the correlation matrix, that can teach you a lot about the importance of specific degrees of freedom. So you can easily generalize this to a larger matrix than just this 2 by 2 matrix, which we had here. Now, I hope this is not too boring here, but I wanted to go through these topics using slides. What the next thing is, if you look at the covariance matrix, this is nothing but the expectation value of xt times x. Now, x is actually x here is a deterministic matrix, because everything which we plug in here is now defined, and we make this assumption that x is not a stochastic variable. So means that every element in the columns and the rows here are just deterministic values. So you could think of you having made a measurement and that all the parameters are well determined. So it's pretty common to have a design matrix which is deterministic, which means then that when we take the expectation value of this matrix, what we would have then is the following. So when we now are calculating the eigenvalues of this matrix, what you could think of is that we perform a orthogonal transformation of the covariance. So what we are doing now is that we take the matrix which we have here and perform a similarity or an orthogonal transformation. And what we can show then is that when we perform this orthogonal transformation, this corresponds of the matrix X. This simply corresponds to us performing a transformation, an orthogonal transformation. So these are orthogonal matrices. Then we are performing an orthogonal transformation of this matrix here. And if I multiply with S from the left, then what I'm getting is that S times this matrix C of Y is given by C of X times S. Now, this matrix here, when we now perform the diagonal transformation, what we have assumed now is that this matrix C of Y, which you see, is diagonal. So we have performed a transformation which now diagonalizes this matrix. So C of Y simply contains the diagonal or the eigenvalues. So it's a diagonal matrix. So what this actually means is that C of Y is diagonal, and then we have an eigenvalue problem of the covariance matrix, where these matrix elements acting, which now contains one specific vector, so this is a column vector acting on the eigenvalue, is now given by the covariance matrix multiplied with this vector S of I. So S of I is just one of the column vectors of this orthogonal matrix, as you can see up here. So this is the matrix which we have. And these are the so-called orthogonal vectors of the matrix S. And you can show that since it's an orthogonal matrix, then if I take the inner product of Si with Sj, this has to be equal to 0, unless I is equal to j. So in the derivation of the PCA theorem, which is the next part, we are actually going to assume that the eigenvalues are ordered in a descending order here. So that means that the largest ones comes first, lambda 0, larger than lambda 1, etc., up to lambda p minus 1. So the eigenvalues, they obviously tell us how much we need to stretch the corresponding eigenvectors. And dimensions with large eigenvalues, they have thus large variations, which means large variance. So large variations leads to large variance, and define therefore useful dimensions. So if you have a large variance, it means that the result will fluctuate much more along a specific axis, for instance. So large variance means that a specific component has a larger fluctuation. And you can see that now immediately. If we just go down a little bit, there is a simple example which we have here with a very simple example. So what we are setting up now is a covariance matrix. So where I now define the covariance and the mean values here. And I'm assuming now that I have x values which are given by this specific mean value. So one of the vectors has a mean value -1, the other one has a mean value of 2. And then I have a covariance 4 for the first one, which means that it has a large variance. And same with the second one, has a large variance of 2. And then I simply construct a normal distribution for these two vectors. So this is a multivariate normal distribution with these parameters here. So if I run that one, what I get now is, first, if I now want to rewrite this, I'm now rewriting this in terms of the scale matrix elements, which I defined earlier. I'm using pandas here. So that's a kind of scaling. And I'm centering my data. And I compute now the covariance. And if I print the covariance here, you will now see that the covariance has eigenvalues, which are close. So I'm not getting the exact covariance because I have a limited data set. So if I increase the data set to, let's say, 100,000 here, then I'm going to get, with the data I generate for the distribution, I'm going to get a covariance then, which is closer to 4 and 2. And you can see that here. So the results are a little bit better than what I had previously. Then what you can do then is to extract the relevant columns from the centered matrix. And what you see here is that since the covariance is pretty large, what you get then is that the results are much scattered along this diagonal here. So this is just an indication that if you look at the data, I have a large spread in the y direction and I have a large spread in the x direction. And that simply tells me that I have a large variance in the x direction and a large variance in the y direction, and they are strongly correlated. So what I could do now is to regenerate this data, but I could make a much larger value here. I could put this one to 10, and then I could put this one to 0.2. So I'm making a smaller covariance, and then I could reduce this one just to 1. So let's just recalculate things here. Just redo it. And what you will see then is that actually the data will show a much smaller covariance or variance in one direction. So if you now plot it, what you see now is that you have a large variance in this direction and you have a smaller variance in this direction. And the covariance is also smaller, as you can see here. This is 0.2, the variance is 9, and this is 0.9 here. So that simply means that maybe if we can squeeze this a little bit further, that we can reduce the dimensionality to just the x-axis here, because this is where we have the largest variance. So when I diagonalize this matrix, which you have here, so this is just a covariance matrix. If I diagonalize it, then clearly this is going to be the dominant eigenvalue, and this is a small eigenvalue. You can see now that if I play around a little bit more with it and I reduce even more the variance here, so suppose I have a very small one, and I make a small correlation between the two data sets, or the two column vectors. If I do that, and just rerun everything, what you will see then is something which looks like this. So this simply tells us now that there is basically no variation along the y-axis, whereas all the variation takes place in the x-axis. And we could now simply say that since this is this much squeezed, we could ignore the y direction as a degree of freedom and simply take care of the x direction, because this is where we have the largest scatter. So the principal value approximation deals actually with this. So you're now going to, what we did here is just by the eye. We see now that we have less variation in the y-axis. And we could say now that when we're going to describe the data, since we have less variation in the y-axis, we could actually skip this as a degree of freedom. So if we now go back after these simple demonstrations here, if we now go back to the PCA theorem, so what the PCA theorem actually says is that we assume that the eigenvalues are ordered this ways. The eigenvalues tell us how much we need, as you saw from the example, to stretch the eigenvectors. And dimensions with large eigenvalues, the x-axis in our case, have thus large variations and large variance, and define therefore what we will call useful dimensions. So if you have something which doesn't vary, it means basically that this is a degree of freedom which is well established. There's basically no uncertainty. If you have a large uncertainty, then we would have to consider that degree of freedom in more detail. And the data points are more spread out in the direction of these eigenvectors, as you saw from the covariance matrix. And smaller eigenvalues mean that the corresponding eigenvectors are shrunk accordingly, as you saw for the y directions. And the data points are then tightly bunched together, and there is not much variation in these specific directions. And hopefully this is something we can use then to reduce the dimensionality of the problem. So if we have a huge dimension P, then you could aim at reducing P to some dimension L, which is much, much smaller than P. And you keep only these features, those features which have the largest variance. Now, you have to remember one thing now. When you diagonalize, this is something where you have to be a little bit careful, because like in this case, we're just studying the covariance matrix. When we diagonalize this matrix, then what happens is that we get a matrix which is diagonal. So that means that this eigenvector for the first state will be mixed with a second eigenvector. Now, if the covariance is small, there will be a small mixing. And then looking at the coefficients of the eigenvectors, then we can simply say that the dominant feature is the x-axis. And then we can leave out the y-axis. However, if you have strong correlations, that means strong covariance, then that means that we have a stronger mixing between the different eigenvectors. And then a specific feature would be a linear combination of several features, but there will be a dominating feature. This case is extreme because we put the covariance to be very small. So in the PCA then, if we go back, here comes the algorithm before we look at the theorem. So we would then simply set up the data points for the design matrix. And then we have the features and then the samples along the rows. Center the data by subtracting the mean value for each column. And this leads to a new matrix. You compute the covariance or correlation matrix, whatever you prefer. And then you find the eigenpairs of C with eigenvalues and eigenvectors. And then you order the eigenvalues and the eigenvectors accordingly in order of decreasing eigenvalues. And then you keep only those L eigenvalues which are larger than a selected threshold value. And that means that you discard the P minus L features, since we expect small variations in the data here. So just keep this in mind, this strong link between the covariance and the kind of features which you want to keep. So PCA is you taking the covariance matrix and just studying that one, and then figuring out which features are the most important. This brings us also back to one of the main axes or main aims in standard machine learning. So in standard machine learning, you want to understand correlations among the features, and you want to make predictions. So prediction is actually us fitting some model to the data. But then the covariance and the correlation matrix, they give us information about how strongly correlated variables are and how much they will fluctuate and vary in one specific direction. So if you now take the proceed a little bit here, so after this simple example which we looked at, so the what you would typically do then is that you solve the find the principal component, so to diagonalize the covariance matrix, and in this case you can use your lin-alg eigenfunction to do that. You compute a percentage of the total variance captured by the first principal component, and then you can plot the mean center data in lines along the first and second principal components, and then you project the mean center data onto the first and second principal components, and then you can plot the projected data. And then that means that you are going to approximate the data in terms of something which runs like this, where V0 is the first principal component. So what you're doing now is to prepare the ground for constructing something which is called the reconstruction error. So that means that now we are going to look at the difference between the original data set and the truncated data set. And the error you make then is going to define your construction error, and that's the quantity you want to optimize. That quantity is going to be the same which you get when you do the linear approximation in the autoencoders. And this is something which I'm going to go through in more detail next week. So what I wanted to bring up first is the basic principal component approach. And then next week, we are going to look at the PCA theorem. And then we're going to construct something which is called the construction error. And this is going to be equal or similar to the mean squared error. And then we can, with a result which is constructed with the first principal component, then we can ask ourselves how big is the error. And then we could proceed with the second adding the second principal component, then adding the third one, etc., till the construction error is as small as we want it. So instead of calculating the mean squared error here, we are going to calculate next week the construction error. And this is something which we will do through the whiteboard. So the PCA theorem, which you see here, we will start there next week and show the link with the standard autoencoder approximation, where we make this linear transformation, where the linear transformation reduces the dimensionality between the input and the hidden layer through this encoding function. And then next week, after we've gone through these details, we are going to look at codes for the autoencoders and how we can actually implement the solution of the differential equations which we have at hand. So I'm going to stop a little bit earlier because the connection or with the PCA theorem and the autoencoders is something which I would need another 10-15 minutes to do. So I hope you can forgive me if we just stop 1 or 2 minutes before time here. But that's something I want to wrap up in the beginning of next week. And then we are also going to look at the codes for the autoencoders. And then we will discuss the project. And then the week thereafter, we are going to start with GANs and see how they can be implemented to solve the same problem.